Hello and welcome back to another installment of the U of A Graduate Student Seminars. Today I'm very excited to have two individuals from the Nuclear Waste Management Organization. For those of you who are not familiar with the NWMO, they are tasked with implementing the Adaptive Phase Management Program, which is the federal government's approved plan for the long-term care of Canada's used nuclear fuel. Of particular interest to us geotechnical and geoenvironmental practitioners is their goal of storing used nuclear fuel in deep geologic repositories, which will be touched on today during their presentation. Before I introduce our speakers, I just want to thank all of the industry, academic, and student presenters who put their names forward to present this year. We had an influx of student volunteers these past weeks, and I'm happy to say that our schedule is now full. If there are still students who wish to present, however, we could potentially try and organize two speakers in one seminar session, or we could arrange a special presentation time to help support your request. So today we have Drs. Monique Hobbs and Hossein Kasani. Monique is a professional geoscientist with over 25 years of experience in Canada and abroad. Monique acquired a PhD from the University of Waterloo in hydrogeochemistry, after which she completed a postdoctoral fellowship in the rock-water interaction group at the University of Bern in Switzerland. She then joined the Geoscience Research Program team in Canada, where she has since conducted and led geoscientific research programs to support nuclear waste management. Monique is currently the lead for the Geoscientific Research and Development Program for NWMO. Some of you may already know Hossein, as before joining NWMO, he completed both his PhD and postdoctoral fellowship here at the U of A with a focus on geomechanics. Hossein is currently a senior geomechanics engineer with NWMO and is tasked with managing the geomechanical research program, as well as supporting their site investigation drilling program through testing of rock cores to determine their geomechanical, thermal, and petrophysical properties. Hossein's areas of expertise include geotechnical and geomechanical engineering, in particular modeling of thermal, hydro-mechanical processes in sedimentary and crystalline rocks, conventional high-temperature lab geomechanical testing, field experiments, and soil mechanics. Please join me in welcoming Monique and Hossein. Monique, I think you're muted.
Right, so I was. Thank you. Hossein, would you just advance the slides?
Sure, for all of them?
Yeah.
Okay.
If you don't mind.
Not at all.
Okay. Thanks very much, Kevin. So if we just go to the next slide. Thank you. So nuclear waste management in Canada actually has quite a long history. But today, for the purpose of today's presentation, I'm going to start where the Nuclear Waste Management Organization started, which is when we were founded in 2002 under the Nuclear Waste Fuel Act. And Kevin already nicely explained a little bit about what our mandate is. Thank you for that. So we were the organization that was, as I mentioned, we were founded in 2002, and we were tasked with engaging with Canadians to have a dialogue about how we should go about managing used fuel. So that's the high level radioactive waste that comes out of the reactors, the fuel for the reactors. Come up with, so that is really was called a study of alternatives. We'll talk more a bit about that in a moment. And then based on that study, we were to propose an approach to the Canadian government, which we did. And then the federal government made a decision on how Canada would proceed with waste management. And then we are also responsible for implementing this plan. Next slide, please. Okay, so the first part was the study of alternatives, as I mentioned. And these are really the key things that we heard from Canadians. First is that safety and security is the absolute top priority when it comes to managing nuclear waste. And because we are the generations that are benefiting from this waste, we have a responsibility to take action and come up with a plan and actually begin to implement it to care for this used fuel. And the approach should be consistent with international best practice and should also be adaptable. Next slide. So after having these dialogues with Canadians between 2002 and 2005, the the approach that the NWMO developed and recommended was called adaptive phase management. And it includes both a technical method, which is a deep geologic repository for the used fuel. And it also, but it's not just a technical solution, it's also a management program. So that includes, I really wanted to highlight two parts here. One is that we need to be, one of the things we heard loud and clear from Canadians is we do need to be responsive to advances in technology, research, Indigenous knowledge, and also changes in societal values with time. And also, also very importantly was that we needed to develop an open, inclusive, and fair siting process. So we put this adaptive phase management plan before the government in 2005, and in 2007 they approved it, at which point we began to develop a siting process. So if you could advance the slide. So we did, again, in dialogue with Canadians, so seeking public input, we developed a siting process, and then in 2010, we launched the site selection process. And this map shows the 22 communities, much to our surprise, that came forward to learn about this project. So it is Canada's largest national infrastructure project. And there was initially a lot of interest in learning about the project. So these are the communities, 3 in Saskatchewan and the remainder in Ontario, who came forward. And since 2010, NWMO has been doing various scientific studies, geoscientific studies, also working with the communities to understand if this project fits with their vision for their own community. And through that, over that time, we've been gradually narrowing down the number of communities that we're working with. So I wanted to mention at this point that the communities can opt out of the process at any time. So it's a stepped, phased process whereby we do some research, we do work in the area, and then we report back to them. And then at each point, at each step, the community has the option of continuing or deciding not to continue. And similarly, we've been trying to look for the communities with the highest potential for this project. So we're currently still studying 2 communities. The number 5 on the map is Ignace, Wabigoon area in northwestern Ontario, and that's in crystalline rock. And then number 21 is in sedimentary rock. Next slide. So this is just a quick schematic to show the deep geologic concept, where the number 1 is on the schematic. You can see the surface facilities. Number 2 shows the shafts that go down into the repository. And then there's a simplified schematic showing the tunnels, which lead to emplacement rooms. And then this figure, the blowout there, is showing the multi-barrier system. And all of these systems are designed to work together such that we isolate and contain the used fuel. That's the key goal here. And so the different barriers are shown, the used fuel itself, the steel lined container, which is coated with copper, and then the bentonite buffer box around the container center. Okay, next slide. Okay, I just wanted to briefly introduce the life cycle of a deep geologic repository and quickly step through the stages. So right now we're in the very first stage, which is select a site and characterize it. So we haven't yet selected a site. We still have 2 communities in the process. And then we will need to submit an application to the Canadian Nuclear Safety Commission in order to apply for a license to prepare the site and also to construct the site. And then at some time later, when we're granted the license, after we've prepared the site, for example, or began to construct the repository, at some point we will have to submit another license to operate and monitor. So what this is showing is essentially there are several stages, and at each stage, before we can move on to the next part of the life cycle of the repository, we have to apply for a license. And so part of the purpose of our research program, ongoing research, is to make sure that we're always bringing the latest science to support and underpin the safety of the, and to assess the safety of the repository. Next, please. So the applied geoscience research supports our site investigations. I'll talk briefly about that in a minute. Also safety assessment, repository design and engineering. We also have a commitment in our organization to interweave Indigenous knowledge. So this really gives us a different lens through which to look at and assess the safety of the repository in addition to the science and the technical lens that we normally use as scientists. So that is just strengthens our program. And then we also are looking to develop the next generation of experts, because this is a very long project, occurs over many generations. And so we'll need to maintain expertise both in-house and also in the academic community for people who are familiar with the project. Next, please. So who conducts this research? In addition to the in-house experts that we have, we also have a large team of academics, universities who are involved in the program, as you can see here. And I'd just like to touch on that several of these universities, including the University of Alberta, are not just involved doing research in our program, but they're also supporting our site investigations work. And then we also collaborate with international organizations, our sister organizations in Finland, Posiva, in Sweden, SKB, and in Switzerland, NAGRA, and in France, ANDRA, so as well as geological surveys. So it's quite a broad scope of experts that we bring to the project. Next. Okay, these are just some examples. This is not a comprehensive list, but it's some examples of international collaboration. And in particular, I wanted to point out the international collaborations that we have with underground research labs. So ASPA in Sweden, Onkalo in Finland, and then also with the Monterey project in Switzerland. So these are facilities where there are underground, you can conduct experiments underground, you can test new methods. And we use these also to develop methods that can be used to conduct verification studies once we're actually underground, once we've started to construct the repository. Next. So two main purposes. We're still conducting research in both crystalline and sedimentary rock because we still have communities in both these environments. And really the purpose of the research is twofold, focused on developing new techniques, methods, and approaches for characterizing the properties of the geosphere. Note that the rocks that we're looking for are extremely low permeability, low porosity, and that makes them challenging to characterize those properties. And also fewer other industries are interested in these types of rocks. So that's part of the focus there. And then also to continue to advance our understanding of how the geosphere will behave in the long term and how that will influence the repository. Next. So now I'll just briefly go over some of the geosphere properties that we look at. I've given several examples here related to geological setting and structure, and I wanted to highlight this particular example shown in the figure. This is work that's being done at Lakehead University, and it's in the Wabigoon subprovince in the regional area where the Ignace community is located. And it's a study looking at hydrothermal alteration to understand the connection between structure and hydrothermal alteration. And that work is being done through our research program. Next, please. Again, some more examples. I'm not going to go through them all, but that just highlight the hydrogeologic properties, some work that was done recently at the University of Waterloo and is currently in publication. And that's the figure shown there at the top is looking at the Canadian Shield. It was a literature study looking at how permeability in fracture zones changes as a function of depth. So this gives us build some understanding, and below that in the lower figure you can see a probability density function. We can look at or make even some guesses, educated guesses based on this about how permeability will change with depth, and we can then compare it to our site-specific data. We also do research related to understanding the hydrogeochemical conditions. Next. So other things in particular to support safety assessment work, we also have research ongoing on different transport properties and geomechanical and thermal properties, which will be of the most interest to this particular group, and that's what Hossein will talk in more detail about momentarily. Next. In terms of long-term geosphere stability, the largest perturbation that we expect in the future to the repository or potential perturbation would be the next glacial cycle, which at this point could be quite delayed, but we still expect that in approximately 60,000 years from now, the glaciers will return to North America. And so therefore we have to assess and understand what the impact of that could be potentially on repository stability. So we have several studies ongoing to that to understand the boundary conditions associated with surface boundary conditions with glaciation, erosion of crystalline rocks. That's a study going on right now at Dalhousie University. And then we also look at groundwater system evolution. How will that change as the climate changes? Next. And then also, of course, seismicity, earthquakes. So these could, we have an ongoing monitoring program at, which we support. It's actually the Canadian Hazard Information Systems at NRCan, which has this monitoring program in Northern Ontario. We support that program. So we can get updated recurrence curves to understand the potential frequency and magnitude of earthquakes. And we also conduct work with the Geological Survey of Canada, support their research to understand and assess the probability and also magnitude of earthquakes that have occurred associated with past glaciation events. And that's what this figure here is showing. It's a study that was done at the border between Eastern Ontario and Quebec. And the colored lake bottoms are showing mass transport deposits, which were, because their signature could be correlated over a very large area, were shown to most likely have been caused by an earthquake about 9,900 years ago when the glaciers were retreating. And then we also look at the geomechanical stability of a repository, which Hossein will now tell you more about the geotechnical aspects of the project.
Thanks, Monique. So I'm going to be providing an overview of our recent and ongoing research programs in geomechanics to support the APM program. The next two slides, I'm providing a summary of all the research programs, and then the following slides will present some of the research results from each program. Our research program is trying to understand and characterize rock behavior at different scales. So as Monique mentioned, we are dealing with two potential low porosity rocks, one in crystalline setting and one is in sedimentary setting. So we are trying to understand, to characterize these two low porosity rocks, and also to understand the geomechanical responses of the rock mass to repository in a long time frame, up to 1 million years. So that's why the research program here includes different teams from numerical modeling, which color-coded in blue here, lab scale modeling, which is in yellow, and field scale modeling in green, and regional scale modeling in brown. So just to walk through briefly through this table, the first program is excavation damage zone, or EDZ, at Queen's University. Next one is the synthetic rock mass program, which was a joint initiative with from University of Alberta and Queen's University. And next one is THM couple modeling, which was done by Itasca to predict repository behavior within 1 million year time frame. Next one was a fault reactivation after glacial unloading. And we have a research program with a research center in France, which is called Fractory, and SKB, the Swedish counterpart, and Posiva, the Finnish counterpart of NWMO, to upscale rock mass properties from a DFN approach. And the next program is fracture parameterization at different scales. And we also have THM characterization of rocks at McGill University, and time-dependent strengths and creep as well. Also, we are having a research program on in-situ stress characterization and quantification of in-situ stress variability at University of Toronto. Next program is the shear-induced pore pressure and ground deformation in argillaceous formations, which is being done by University of Alberta and jointly sponsored by NAGRA from Switzerland. And we have a program in which compiled the local regional in-situ stress magnitudes and orientation in the Canadian Shield. And we're also involved in Monterey Underground Research Lab field experiments. And we are also sponsoring the University of Alberta's NSERC Energy Simulation IRC Research Chair Program in reservoir geomechanics. So this slide shows some highlights from the excavation damage zone research program at Queen's University. This is a summary of some highlights from the numerical modeling part. Queen's University has been trying to study EDZ delineation from different approaches using continuum, discontinuum, and hybrid modeling approach. In this cartoon on the upper right corner, you see a tunnel, and the rock mass includes some fracture networks, the fracture sets in red and green. And so the highlight here is the gray, dark gray area, which is called highly damaged zone in the vicinity of the excavation. And then the medium gray zone, which is excavation damage zone, and the light gray is excavation influence zone. Queen's University also have been trying to assess the reliability of EDZ predictions, and also trying to back analyze some of the field measurements, some of the mine-by experiments documented in literature. Also trying to numerically upscale modeling process from rock core scale to tunnel scale, and also conducting some creep modeling as well. So as one example, in the bottom right, you see the one of the ACL tunnels and the damage zone, the notches on the top and bottom. And this modeling was able to match the damage zone numerically compared to what observed in situ. Queen's University has also been trying to run laboratory experiments to characterize Coburg limestone and lactobonite granite. Coburg limestone is the proposed host rock for the Southern Ontario potential DGR. And lactobonite granite is a reference rock from the Canadian Shield, although our site investigation is continuing in another rock type, not exactly lactobonite granite. But NWMO has provided these two blocks of two type of rock and to be studied by different universities. Queen's is trying to understand the effect of saturation or resaturation or desaturation on rock mechanics, effect of loading rate on other parameters on rock strength and stiffness. In the bottom right corner, you see some example results. Red symbols are UCS values achieved from testing rocks at different water content, which is shown in the horizontal axis. Even though the water content is very low, you see that as water content increased, UCS value decreased. The middle data, the rectangles are crack damage threshold, and the yellow symbols are crack initiation threshold. Other testing pertinent to EDZ or fracture characterization have been ongoing at Queen's University as well. For example, studying joint shear properties under different boundary conditions, such as CNS, constant normal stiffness, or constant normal loading condition. In the bottom left corner, you see a photo of a granitic rock being prepared for UCS testing. You see that there are LVDT systems attached to the sample, which are measuring both axial and radial deformation. Also, the sample has been surrounded by lines of fiber optic sensors, which is wrapped around the sample, because as we know, fiber optic sensors can provide a continuous record of the sample strains. However, LVDTs only provide the localized measurements. This slide shows some results from another study which was done at ETH Zurich in Switzerland. Time-dependent strengths of Coburg limestone was studied here. So on the vertical axis, you see driving stress ratios, which is the ratio of the existing axial stress being applied on the sample divided by the average UCS of that rock type. On the horizontal axis, you see log of time in seconds. There are three zones here, distinct zones in this plot. The first zone is zone of no failure. If you load your rock sample under a crack initiation stress threshold, so the sample is not going to fail. And if you load the rock between the crack initiation and crack damage stress threshold, so this zone is very uncertain. So depending on the magnitude of load, the sample may fail or may not fail. And the upper zone is the zone which you load the sample above the crack damage stress threshold. And in this zone, failure is inevitable. This study in particular tested one rock sample from Coburg limestone with a driving stress ratio of around 70%. And even after 1 year, the sample did not fail. So the research program at McGill University is also working on Coburg limestone and lactobonite granite. However, the focus of activities are a little bit different. McGill is trying to characterize the thermo-hydromechanical properties of these two types of rock. In the bottom, you see pictures of Coburg limestone, and all these pictures are from Coburg limestone. You see that there are dark gray zones and light gray zones. So the dark gray zones are argillaceous species which contain more clay content. The light gray portion is calcite-rich species. In this study, the sample was dissected into smaller discs, and photographic records of both faces of each disc was taken, and they were compiled together to provide an aerial realization of the two species in the rock mass. McGill University also is studying the stress strain and deformation and overall mechanical properties of these rocks. They're also measuring poroelastic properties which are required for THM couple modeling, properties such as Bu's effective stress coefficient, Skempton's pore pressure coefficient. They're also developing indirect methods to approximate these properties using the mineralogical composition of each dark and light gray species. And they're also measuring thermal properties such as thermal conductivity using different methods, and also trying to approximate these properties from mineral content. They're also measuring permeability of these low porosity rocks from different methods, steady state versus pulse decay, as well trying to approximate the permeability of the rock mass. In the bottom right corner, you see a large triaxial apparatus which was sponsored by NWMO through this research program. So this the need was due to the heterogeneity observed in Coburg limestone. This large triaxial apparatus can accommodate samples 150 millimeter in diameter. This is, I think I'm not using the updated slides, but I'm going to continue. My apologies about that. So this is a joint program which was finished a few years ago by Queen's University and University of Alberta, called Synthetic Rock Mass. The objective was to develop numerical modeling methodology to simulate rock response at different scales, from core scale all the way to tunnel scale. Long-term stability analysis of a potential repository. So the idea is to understand the rock mass response to nuclear waste disposal in both crystalline and sedimentary rock setting over a time frame of 1 million years. And we model different loading scenarios, anything from thermal loading, seismic loading, glacial loading and unloading, and potential scenarios where internal gas is generated due to useful container corrosion. This slide includes two scales of modeling. So in the bottom, in the middle, you see the small scale model, which is focused on around the emplacement room. The model dimensions in the scale of meters, 20, 30 meters. And we call this near field model. The upper right corner, you see the far field model. The model dimensions are in the order of kilometers. And we do continuum modeling or discontinuum modeling. For example, in the bottom left corner, you see a result of a discontinuum modeling trying to assess the extent of excavation damage zone around the opening. One highlight from this type of modeling is we must know the temperature time evolution of our potential DGR. So on the vertical axis, you have temperature, horizontal axis, you have time in years. And let's focus on the red curve here, which shows the temperature with time at the roof of a placement room, so which is around 80 something degrees Celsius. So as you can observe, the peak temperature will occur after 40 something years post closure. And the rock mass temperature remains at an elevated temperature condition for the next hundreds and thousands of years. After 100,000 of years, so the temperature will go back to ambient condition. Another output of this modeling would be assessing the maximum loading magnitude on the useful container, which is required for mechanical design of the container. Previous modelings were focused on NWMO's case studies. Future modeling, however, will be site-specific. This is a study was done by Itasca recently, and it simulated the fault reactivation scenarios. So you see that there's a fault at some 30 or 40 degree angle to the horizontal. And that fault is crossing a discrete fracture network zone. And this site was assumed to be in Northern Ontario under high in situ stress conditions. Earthquake magnitude of 6.1 to 6.9 was applied to this model. And in the bottom corner, in the bottom left, you see that the fault displacement is shown here, which is in the order of 2 meters, the maximum displacement in a red area. In the bottom right corner, you see displacement of each fracture. So different curves are showing a different distance from the fault surface. So let's focus on the orange curve here, which showing the fracture displacement for those fractures contained within 0 to 200 meters from the fault surface. So from this figure, for example, we can say 65% of the fractures in 0 to 200 meters has slipped more than 5 centimeters. So the 5 centimeter is the container allowable shear displacement from SKB. So we are still developing our own container allowable shear displacement. but this type of analysis can help us assess the respect distance that we need to take from the fault surface. Previous analysis were done for NWMO's case study. However, future analysis will be done using site-specific discrete fraction network and rock properties. Next project is rock mass effective properties. This is a purely numerical modeling research program. The objective here was to bridge the gap between complex SR synthetic rock mass modeling and the simplistic representation of the same with conventional rock mass classification approaches. So to put it in another word, we are trying to develop numerical routes for upscaling rock mass properties. First phase of the program was focused on elastic properties. The second phase, which is the ongoing phase, is focused on strength properties. So to explain what this model does, let's focus on the fracture sets in the stereo net on the right side of the slide here. These were taken from a Forsmark site in Sweden. And this research program uses analytical and numerical methods to upscale elastic properties. So to be able to do this upscaling, we need to populate the fracture networks in our model. These are usually assumed disk-shaped fractures. We need to assign fracture properties, shear stiffness of the fracture, normal stiffness, and if they are critically stressed, we need to assign friction angle. And we also know that we also need to know the volume of our fracture rock. As well, we need to input intact rock properties such as Young's modulus and Poisson's ratio. Last but not least, the in situ stress condition should be known. So the plot on the left side shows rock mass equivalent elastic modulus versus model dimensions. So these were done on models with different dimensions, anything from a few meters up to 20 meters for two different assumptions. Red symbols are for cases where shear stiffness of the fractures were assumed 0, whereas the blue symbols are for the cases where shear stiffness was a function of a normal stress acting on the fracture plane. As you see, as we increase the model dimension, Young's modulus of the rock mass decreases. However, at a dimension of 20 meters or so, the effect of DFN is diminished. And just to remind everybody that the the intact rock Young's modulus was 67.9. For example, for models containing 20 meter in dimensions of the rock mass, Young's modulus was around 62.5, which was a significant decrease. NWMO is joining another aspect of these rock mass properties from a DFN approach, which is upscaling rock mass permeability. However, as I said, we are in the process of joining this program, and I'm not presenting anything here today. Oh, sorry. So I'm not using the updated slides, so I'm going to skip this one. This program is called POST program, which is a joint collaboration between Research Institute of Sweden, SKB, our Swedish counterpart, KTH in Sweden, and Posiva, the Finnish nuclear waste management organization. Posiva was only involved in phase 1 of the program. At the moment, we are in phase 3 of the research program. The idea was to measure shear properties of fractures at different scales, at 3 scales, and to manufacture a large shear box, which can test samples 50 centimeter in length. The machine is already operational, and the preliminary test results are very promising. The back analysis of different scales of shear tests will be future phases of the project. We are also involved in situ experiments at Mount Terry Underground Research Lab. This one is a long-term monitoring of the Foley scale emplacement experiment. In the bottom right corner, you see a tunnel which is 50 meters in length, and there are 3 heaters embedded. So on the top right, you see one of the heaters before installation. There are several boreholes drilled and equipped with different sensors in different orientations to monitor and to capture the bentonite and host rock response to THM coupled effects induced by the repository. This is the entrance of the FEA experiment. So at the moment, there is a modeling task force consists of 4 different teams from around the globe doing the modeling, trying to match the THM behavior of the repository. I need to mention that the heating was started in December 2014 and is planned to continue until December 2022. At the moment, the modeling teams are trying to capture the responses observed in situ. However, future modeling practice will focus on prediction of the future scenario, what will happen after 20, 30, or 50 years of the program. GCA is another field experiment that NWMO is involved. This experiment is trying to understand rock response or excavation response if when the transition is happening from sandy to shaly facies. Daily measurements of pore pressure and conversions of the tunnel was done. The other component of the research program included analyzing lab statistical measurements and field dynamic properties of the Apollonius clay and other formations. And I need to highlight that the University of Alberta is also involved in conducting in situ stress measurement using their reservoir geomechanics pressure meter tool. This is a new research program at the University of Alberta that Kevin is conducting. So the research question here was why conventional modeling cannot properly capture tunnel behavior in situ. So the hypothesis is that the question might lie in how we measure pore pressure. So the research program has installed gravity-in piezometers in situ, and also trying to measure pore pressure in the lab differently by using fiber optic sensors in a triaxial and direct shear apparatus. The final goal of this research program will be integrating lab data and field data and trying to better match the tunnel behavior in situ. Speaking of in situ stress, this is a compilation study by Morocco done for NWMO recently. More than 200 cases of in situ stress measurements were collected from the Canadian Shield and analyzed. So this study provided us with average estimates of maximum, minimum horizontal stresses and vertical stresses in the Canadian Shield, as well as their orientations. This new research program is being done at the University of Toronto, trying to quantify the variability of in situ stresses. The program started in 2020 and trying to do a statistical analysis using a Bayesian approach. So the challenge here is usually we get a small number of in situ stress measurements. However, this small number of data are variable mostly due to complexities because of the geological environment. This is a PhD program, and in a Bayesian statistical approach, many parameters are also considered variable, whereas in a conventional statistical analysis, which is frequentist analysis, we usually assume that the mean value is fixed. This research program is trying to take a tensorial approach, try to better constrain principal stress magnitudes and orientations. And the final outcome of this project will be a protocol that can be applied to any site. However, for developing that protocol, the research program is intending to use some in situ stress measurements data from SKB to develop the methodology. As previously mentioned, NWMO joined the University of Alberta NSERC Energy Simulation IRC in reservoir geomechanics. And this research program is sponsoring several graduate students and postdocs and trying to understand sedimentary rock behavior at different scales, from pore scale to core scale to reservoir scale. This includes lab experimental studies, numerical modeling, and centrifuge and pressure meter testing. And we are hoping to be able to advance our understanding of how sedimentary and crystalline rock respond to nuclear waste disposal. So I showed, in the previous slide, I showed for long-term stability analysis, one scenario, loading scenario is the glacial loading. This research program tried to use the University of Toronto glacial system model and estimate changes in vertical in situ stress, maximum and minimum principal stresses, horizontal stresses during glacial loading. This information is required for long-term stability analysis, especially when we are dealing with glacial loading scenario. Also, this information will support the fault reactivation and modeling studies. And that's all from me. Thank you.
Thank you, Dr. Monique and Dr. Hossein, for your great presentations. I'm going to be the moderator for the Q&A session. And sorry about that, we already run out of time because of the technical difficulties at the beginning. But we thank you for introducing the programs and sharing your experience and knowledge with us. Sounds like there are still lots of challenges we have to face, but I'm sure this creates some opportunities for researchers like us in the future. And we have some questions coming up in the chat. The first one is from Ali Reza. And he asks, speaking of long-term stability of nuclear waste repository, what are the current monitoring protocols based on to ensure the safety of these subsurface repositories? It's based on deformation first or radiation first?
I'm just looking at the question. Okay, so I'll take a stab at this. And I think if I understood your question correctly, we're, so when we put an application in for a license for a repository, it's based on a safety case, what we call a safety case, which brings together all the arguments for safety. And one of the things that that the repository is assessed on is the dose level to the public. So we basically have to assess how some family, for example, if they were to be living directly above the repository 60,000 years in the future, for example, what would the dose be to a family if they were taking their water from well and there was some breach in the repository? What would the dose impact be? So it is based primarily on the release of the safety is assessed to a strong basis. Many different arguments and lines of reasoning are used to understand the safety, but one of the key things that will be evaluated by the CNSC is the dose, and the repository must be below the regulatory limits.
Thank you for explanation, Dr. Monique. I have another question from Kevin. He's asking, like, how can you, so what is the required design life of the Deep Geological Repository and how this drives the research that you're conducting at NWMO?
So we need to demonstrate so the repository would actually be operating for about 40 years. There is a requirement for monitoring. So we do need to monitor the repository. We also need to monitor it after. Whether we monitor, the degree of monitoring to be done after closure will be decided at some time in the future. But the time frame over which we need to assess the safety of the repository is 1 million years.
Great.
That answers the question.
Maybe I can follow up on that actually. Well, in terms of how this drives our research program at NWMO, you saw in some of my slides that we need to do modeling to include all the loading scenarios which may occur in 1 million year time frame. So anything from probable or low probability earthquake to glacial loading, different glacial episodes. And in terms of thermal modeling, we have to run our thermal model for 1 million year time frame, and then study at the same time the coupled processes, the impact on pore pressure, and then rock deformation or failure. In the lab environment, one important factor is for us to understand the long-term strengths. So for long-term modeling, we need to input long-term strengths of the rock. I show in one of the slides that we are trying to, the longest we could go was 1 year. And based on some analytical solutions, we need to extrapolate that strength degradation with time to 1 million year time frame. So this might help.
Thank you for your good answers.
Thanks.
I think now it concludes our seminar. Sorry again for the delay of the seminar, but I appreciate everyone joining us, and also thank you again, Dr. Monique and Dr. Hossein, for giving us such a great presentation. With that,
thank you for the opportunity.
Other announcements from Kevin?
Nope, I just want to say thank you again for the great presentation. Sorry to everyone. And I will announce something. We have another great presenter next week coming up in Gord McKenna, who will be talking about the design of tailings landforms. So everyone come out to that again, and I appreciate you all for sticking around. We had over 50 people in attendance today, which is great. So thank you everyone. And thanks Monique and Hossein again for the great presentation.
Thanks for having us.
Thank you.